Welcome back, everybody. So for the last few days, we've been stepping into the world of differential equations. And today we're going to work on a worksheet that in some ways is a nice reflection on these ideas that we've seen so far. And so let's dive right in. So here we're looking at what's called the logistic equation. And this is an equation that can be used to model populations when we have a situation where we're thinking about an environment that has limited resources. And in general, when we think about, say, populations, we normally want to think of our input variable to our function as being t. It doesn't really matter what letter we call it, but we often want to think about the population with respect to time. And so here we're looking at a specific instance of the logistic equation where the k out front is 1 and the m down at the bottom is 8. And first we're asked to graph the direction field at a certain number of points. And so recall the idea of the direction field is that at each point, say xy right here, or let me say ty, since we're thinking about population, we can, through our differential equation, see what that y prime would have to be there. We can draw a little line segment with slope equal to that y prime. And so here we're given 7 different points to figure out and get a little sketch of a line segment there. And so just taking those one at a time, so for 0, minus 1, we're going to plug in t equals 0, y equals minus 1 to our differential equation. And notice that there's actually no t involved at all with our differential equation, right? So the term that we use is this differential equation is autonomous, right? There's no input variable going on. So we just use our y coordinate here, plug it in at the front and up top, and it works out to be negative 9/8. And similarly, we can go through these other 7 points, I guess other 6 points, and feed in the t and y coordinates and get our slopes, and we end up with what we see here. Now with those on hand, we want to go down and sketch our line segments with those approximate slopes. And so here we have that. At 0 and at 8, we saw the slope of 0. At 4, we got a slope of 2. And so here, notice with the grid that's on this graph, we step over 1, we go up 2, so that's a slope 2 right there. At 7 and at 1, we had this slope of 0.875, so I just tried to draw that positive, but a little bit more mellow than the slope that we had at 4. And then at negative 1 and at 9, we saw this negative slope, negative 9/8. Again, just try to draw it negative. And so with those, we have the line segments sketched in at each of those 7 points. At part B on the worksheet tells us to use the fact that our differential equation is autonomous to quickly kind of get a lot more line segments, right? And so the idea here is that, well, for example, this computation here at 0, 4, if we chose a different t value, let's say t equals 1 or 2 or negative 3 or 10, and kept that same y, our y prime computation would go through the exact same way, right? Because our differential equation doesn't see t at all. We still get 2. And so that means that down here where we see this slope of 2, we can just pick a bunch of points left and right and draw in that same slope. Because at each of those points of that same y value, our differential equation would tell us that we need to have the same slope there. And similarly, all these other line segments, we can just copy paste them left and right. And so here at 0, we have a horizontal tangent line, right, slope 0, and so we can just draw a bunch of those going across. And up here at 8, we have a bunch more horizontal tangents. At 7 and 1, we have these positive but slightly mellow tangents. Sketch those in, and then what color do we want to use next? Purple. We got these negative but slightly mellow slopes at 9 and -1. And with that, we have our nicely colored sketch of the direction fields for our differential equation here. All right, so moving on, the next question is wanting us to plot some solution curves and also put some physical interpretation to our differential equation. So here, we're thinking about modeling a population of insects in a forest. And so our units here, we're saying are thousands of insects. And so let's sketch a few solution curves. I'm starting with the solution curve with initial condition y of 0 equals 1. And so if y of 0 equals 1, that means our solution curve goes to the point 0, 1. So actually right here. And so here is our point 0, 1 that we're based at. And recall the idea of the direction field is that a solution to our differential equation would move through this direction field perfectly, matching the correct slope at each and every point. And so kind of reading off some instructions, starting from this point, we're actually going to match exactly our green slope to start. Then we'll start coming up, and then we'll get a little bit steeper as we get here to the pink region. And then as we move up, we'll mellow out a little bit, and then mellow out some more as we approach the blue lines up here. So kind of putting that together, starting up like that, then a little bit steeper, and then mellowing out, something like that is at least a rough sketch of what this solution would look like. And so here the question asks us, well, what's the limiting behavior of our solution function? The limit of y of t as t goes to infinity. And so here, as t increases, things are mellowing out, and it looks like our y values are approaching 8. The next two parts ask us to play this game again for two different initial conditions, 0, 4 and 0, 10. So putting those on our direction field, 0, 4 is right in the middle, and 0, 10 is up here at the top. And so at 0, 4, again, we're going to be coming up, then mellowing out, so something like this. And at 0, 10, we're going to have a negative slope initially, coming down and then mellowing out again near our blue lines. Something like that. And notice in each case, we're mellowing out, approaching the same y value, y equals 8. And so we're going to get the same limit for each of these solution curves here. Now, how could we interpret this physically? Well, this is somehow saying that our populations of insects, right, that's what are represented by our black curves here, tend towards 8,000 insects and want to stay there. And so a possible way to phrase that is that our forest has a carrying capacity of 8,000 insects. That's what it can naturally support. All right, so next, we talked before about how from direction fields we often can't find exact formulas for solutions, but sometimes if there are straight line solutions, we can spot those in our direction field. And so this is about spotting a couple of those. Using our direction field, can we spot any horizontal solutions? So just constant functions, essentially. And so here, up on our direction field, looking at our horizontal tangents at 8 and at 0, right, if we just moved straight across horizontally, that looks to be moving through our direction field perfectly. And similarly down here at 0. And so it seems like these constant functions of y equals 8 and y equals 0 kind of pass this visual test, but how do we actually take functions and see if they algebraically solve our differential equation? How can we actually check this? If you said plug them into our differential equation, you are absolutely right. All right, this is how we check to see if these solve our differential equation. Our differential equation is just an equation, and so we just need to plug our functions into the left-hand side and right-hand side of this differential equation and make sure that things match up. All right, so here's our differential equation. And so if we want to, say, start with y equals 0, well, then the left-hand side of our differential equation is just y prime. And well, what's the derivative of our constant function 0? It's just 0. Next, on the right-hand side, we just need to plug in our function y wherever we see that y. And so here, we're just plugging in 0 up front and up top. And we get 0 times 1, which is 0. And indeed, our left-hand side equals our right-hand side. So algebraically, we see that the constant function y equals 0 is a solution. And we can play the similar game for the function y equals 8. And the derivative of a constant is 0. And plugging in, we get 8 times 0, which is also 0. And so things match up there as well. All right, and so we often, from our differential equation, it's often very difficult to come up with exact solutions, but here I claim that this differential equation is one that we can actually solve. And right, we only know how to solve one type of differential equation at this point, and so what I'm claiming is that this differential equation is indeed separable. And so we know how to find a family of solutions to a separable differential equation, and we also know how to figure out which member of that family satisfies an initial condition. And this problem is about putting that to work. Now this problem is a challenging one. It's a great bringing together of integration techniques, exponential and log properties, and algebra. And so if you haven't spent much time with this one yet, pause the video and try and work through it, or at certain points through this solution, pause the video if you think that you can make progress from there. It's a great problem. A lot of good stuff in there. All right, well, let's start talking about this. Right, for a separable differential equation, here I'm just taking y prime and rewritten it as dy dt. Right, so we can do our process. And so we want to keep our y stuff up top on the left, and so we'll take our y stuff over here on the right and divide it over to be with the dy. And then dt, we just need to multiply both sides by, bring it over to the right, and we end up with this right here. So our y stuff is on its side, and our t stuff is on its side. There's really no t stuff besides just the dt, and at this point we will integrate. And over here on the right, this looks a little bit goofy. Essentially, we can just think of this as integrating the constant function 1. Right, so over here on the right, we know how to integrate constant functions, and so that one's good to go. But over on the left, how might we integrate this function? So a couple observations here. This function is a rational function. Its denominator is actually nicely factored for us already. And those two things together definitely give a nudge towards partial fractions. And that's going to be what allows us to break this up and integrate it just piece by piece. All right, so how that goes, we use our partial fraction decomposition. So we're going to get a factor corresponding to both this linear factor y and this linear factor 1 minus y. Since those are linear, right, we just need to have constants up top. And then we just need to clear denominators, multiplying both sides by our denominator y times 1 minus y. And when the dust settles, we're left with what we see here. And we just need to figure out what a and b are, and here by plugging in different values for y. And both of these are linear terms, so we have some clean y's that suggest themselves to kill off this b term. We can plug in y equals 0. We end up with a being 1. And similarly, plugging in y equals 1 to kill off this a term, end up with b equals 1 as well. So nice clean coefficients. And so popping those in for a and b up in the numerators, we see that the integral we're left with computing is this right here. And now with our, oops, this should say this b is 1. All right, so let's make that substitution. And each of these integrals, I claim we are now equipped to handle. We can integrate at this point. There's a little subtlety here in the middle. We end up with is natural log of absolute value of y for the left-hand term's antiderivative. And we get minus natural log absolute value of 1 minus y for the middle. And where this minus is coming from is this minus y in the denominator. It needs to be there. Essentially what's going to happen is if we did a u sub to formally and real carefully work out this antiderivative, then we would get that negative coming out from the derivative of our u, would be that -1. So we'd end up with minus integral of 1 over u, so minus natural log of absolute value of u, which gives us our minus natural log absolute value of 1 minus y up here. All right, then over on the right, integrating 1, we get t, and we just toss our constants over on the right with the plus c. And if you look back up the statement of the problem, we are assuming that both y and 1 minus y are positive, which means we can drop the absolute values around those. And so here we get at least a clean starting equation describing a family of solutions to our differential equation. At this point, we have two things left to do from the statement of the problem. If we look back up there, one of the things we wanted to do was figure out which one of these satisfied the initial condition, y of 0 equals 1/2. And also, I think on your sheet, we want to solve for our solution function y explicitly, right, as y some function of t. And one thing to notice is that, so this differential equation we're working with is not the exact same logistic equation that we were working with above. This has still k equals 1, but that m on the bottom is 1 here. Just a little side note. Anyways, so we have two things left to do. Figure out which member of our family satisfies the initial condition, and then solve for y explicitly. We technically could do these in either order, but for us where we are, it turns out it's a little bit cleaner to find the solution to our initial condition first, to figure out which c works. And so let's do that. Right, and the way that that goes is we use our initial condition, and from it we see that, well, our solution function, right, needs to, at t equals 0, have the y value of 1/2. And so we can take those and plug them in for t and y here in our family equation. And so if we do that, things actually cancel nicely. Here on the left, we get natural log of 1/2 repeated. And so things cancel out on the left, and we're left with a nice clean c equals 0. And so with that, we have one last step to do, and that's solve for y explicitly in terms of t, right? And where here is our equation with c equals 0 plugged in. So that's gone. And right now, this equation is just describing y implicitly as a function of t. To get an explicit description, we want to solve for y. And so we have an interesting challenge in front of us, right? We got y's floating around in two different places on the left. And to start doing that, we'd like to somehow get those collected, get those together. Can you think of any way to do that? Right, if only we had some way of taking these two natural logs and like combining them somehow. Oh wait, we do. right? Natural log of A minus natural log of B equals natural log of A over B. Oh yeah, rules of logs. All right, so using that, we get to combine our left-hand side of, in terms of one natural log, and now to get rid of the natural log, we can just exponentiate both sides. And so we get what's here. And so that's nice. Now our y stuff is together, but it's still kind of, I don't know, still kind of separated. We got a y up top and a y at the bottom now. Any ideas as to how we could make progress here and try and solve for y? I think a natural step is just clear denominators, right? We don't want to think about fractions if we don't have to. So we get here, and at this point, I think it's maybe still possibly unclear as to how to move forward. But here we can try and give ourselves a little analogy to work with, right? I think that e to the t maybe weirds us out more than it needs to. And so to give ourselves a little helpful, I don't know, analogy to work with, let's just imagine that this e to the t is just some number. Let's say that it's 7. And we were trying to take this equation here in the bubble and solve it for y. Do you see how you might do that? Well, here I think this is feeling a little bit more manageable, right? What we want to do is take the 7, distribute it through, bring our y stuff to the left-hand side, maybe pull out that common factor and divide by the coefficient. That's exactly what we're going to do here, except instead of 7, we have e to the t. So if we distribute that e to the t to the 1 and the y, and then add the e to the ty to the left-hand side. Now, both of our terms on the left have this factor of y. Pull that out, divide by the coefficient we have, and voila. We have solved explicitly for our solution function to our initial value problem. That's a good one, right? All right. Good work today, everybody. If you have any questions, post those to Piazza, and I'll see you next time.